Hello guys, welcome back to the Black-Scholes Merton European Option Pricing Model derivation, and in this video we're going to be discussing geometric Brownian motion and just putting together everything that has been talked about thus far in the video lecture series. So I want to bring back the analogy of kinematics. In the scenario of a dropping ball, so we knew we had a position function as a function of time, x of t, and that's going to be equal to our initial position plus our initial velocity times time plus 1/2 our acceleration t squared. And I mentioned that we have three free variables, and we can choose these depending on the system that we want to analyze. And in the first video, I was talking about a financial asset equation. Financial asset equation. And if we can do it, how do we do it? And after a few videos, it's evident that we can use geometric Brownian motion. Specifically, in differential form, we are going to have ds is equal to mu s dt plus, not mu, sigma s dw. And in this case, we have our mu, which is our mean returns, and our sigma, which is our volatility. And in the same way we can choose x naught, b naught, and a naught for our kinematic equation, we can choose these to model any financial asset that we so desire. We can model S1, S2, S3, all the way up to Sn, if we so desire. And just to make it clear, for S1 I'll have mu1 and I'll have, so for every case I would have a different mean return and a different volatility. Cool. Now, since we're finished with the model, I want to delve into a little bit of analyzation, right? Now, for what this model really means, just so you guys get a full understanding of what this is, because it is different than the kinematic equation, because instead of just a regular quadratic equation, it's a continuous time stochastic process that's geometric in nature, which is quite a bit more difficult. So let's restate our very important equation. Mu s dt plus omega s dw, right? And then again, as we've been saying, this is our drift term, and this is going to be our shock term, right? And just to go into shock a little bit, this really adds standard deviation values to our model. And why do we choose to do that? Well, for this reason. Stocks are random. Random, yeah. So obviously this is just the drift of where it's going to tend to go. Even if we choose a really good constant for drift, it's not enough information, or it might be enough information, but we can extract more information by adding our shock term. And going off of this, because stocks are random, right, it's more useful to put prices in a probability distribution. And obviously our drift is just our general movement. Cool. So essentially how we can use it is as such. If we have a given stock price until T0, and it looks something like that, and it stops here, and we want to know what happens to the stock moving forward. Well, we can come up with a mean recurrence, right? So this could be our mean recurrence. It's a pretty good one, right? I want to draw lines just to separate what we know and what we don't know. So this is historical data. Right? And from this, we can figure out some mean returns, and we can also find out some kind of volatility. And using these two, we can put it into our differential equation, and we can almost extend this depending on our volatility. We can get some sample paths of, oh, that's not okay, that's okay. Some sample paths of where this could end up. Now, we don't exactly know what the movement of the stock is going to look with a high level of precision, but we have a general idea of where it can be. And this is what we can call our sample paths. Choosing a good mean returns and volatility. And from this, we can essentially calculate our standard deviations. Which is going to be our 64%. And we can also calculate our two standard deviations, which I believe is about 95% accuracy. So stocks are 95% going to fall under that range, right? And so on and so forth. We can also calculate the expected value of our stock price. Cool, so I want to go over the expected value of our stock price a little bit in more detail. So if we want to take, let's say, our expected value, and I'll probably do that over here. Let's call this expected value. So we want to take the expected value of our stock price as a function of time, and that's going to be equal to our expected value of mu s dt plus omega s dw. Cool, so we're going to say that's going to be our expected value of our mu s dt plus the expected value of sigma s dw. Now, we know that the expected value of our Brownian motion, and I just realized I used dw, w standing for the Wiener process, but it's the same thing as dB, right? I just want to make a quick note of that. dB and dw can be used interchangeably. You'll see that pretty often in the literature, but we know that the expected value of our dw, or our expected value of our dB, is going to be equal to 0. So that, therefore, this term cancels out. Essentially what we're left with is our expected value of mu s dt, which has no randomness. Therefore, our expected value for differential of our stock price as a function of time is just going to be our mu s dt, which is just our drift. So we can calculate our standard deviations, or 64%, and we can transition that into 95% if we multiply it by 2 if we so desire. But our expected value of our function is just going to follow this geometric drift. And once we know our geometric drift, and that being our expected value, if we get a point, for example, way off over here, for example in a sample path, if we somehow get a point up here, we know how far that point deviates from the expected value, and we can put that in terms of probability and make financial decisions based off that, right? One thing I want to cover is the necessity of choosing good mu and sigma values, and to kind of show what happens if you don't. So this would be called calibration. Calibration, okay. So in the same way, let's say we have some initial stock, right? Or not represented like that. How about we have some path, And this is what we know. This is going to be our historical data. And this is going to be our forecast. So T, and then this is going to be TO, or what we know so far. This is going to be obviously our stock price as a function of time. Now let's say we hypothetically choose a bad mean returns and a bad sigma, right? So we know that our mean returns is a good one would probably look something like this, and then our volatility is probably quite low, except maybe over here, but generally it tends to be quite low. And so, so these two would be good. Now, just for the sake of an example, let's say I say my mean returns is less than 0, and it's a lot less than 0, and then my volatility is very high. So I choose mean returns as negative 0.8 or something, and then volatility as a very large value. My forecast would look something like this. And then obviously we'd have our standard deviation limits, which we can calculate out. And we can have our expected value of S of t over here. Now, just by looking at this right here, even though we're using the same exact model, this is not a good representation of the stock price we're trying to analyze because we did not choose our mean returns and volatility in a good way. So to make the final point, ds is equal to mu s dt plus sigma s dw is very powerful if mu and sigma are chosen correctly. And generally these terms, mu and sigma, are going to be a lot harder to analyze than, for example, the mass of a ball or the initial height of a ball, a dropping ball. And usually you're going to use some kind of regression model or some kind of machine learning model to really calibrate these parameters properly. And the power doesn't really come from a better model, but it comes from how well you can calibrate the model that you have at hand. Now, there are other models that extend off geometric Brownian motion. There's a Poisson diffusion model, which is another one that follows something called a Poisson process. And then there's also a branch called Levy processes, which is a little bit more advanced. But in terms of the Black-Scholes, the Black-Scholes assumes this, right? Which is why we're really going over this. And this geometric Brownian motion model is used across the industry with many applications, not just the Black-Scholes. But for this case, I just want to state that the Black-Scholes is derived and assumes geometric Brownian motion. So now in the next part, we will be talking about what an option contract is and why geometric Brownian motion is important when finding the fair price of an options contract.